So we've identified how to find zeros using tables and graphs and these visual methods, but now let's also take a look at how we find zeros sort of analytically or algebraically. So let's go back to this function that we've looked at a few times, y equals x cubed plus 2x squared minus 5x minus 6. And to find those zeros that we did on the last page, we used the table, used the graph, and sort of used the equation. So those zeros that we found were x is equal to -3, -1, and 2. So these are the solutions we get when we set y equal to 0. Or in other words, if we plug these x values into the equation for x, we're going to get 0 as the output. And so remember that when we have x equals -3 is the 0, then that means that the factor that's associated to this is x plus 3. So it's just that opposite sign. And we can find these zeros using division, especially if we already have a 0 in hand, because what it means to have a 0, or in other words, we have a factor, x plus 3 is a factor. And just like with numbers, if something is a factor of something else, then that means that you can divide the two things and you get out some nice result, some nice quotient that has no remainder. So to have a factor, it means that it divides, or it goes into the polynomial evenly with no remainder, or a remainder of 0. So there's two ways that we'll see how to divide. The first way is with long division. Just like long division with numbers, but we're going to do long division with polynomials. So with the long division, we use the factor. And remember, the factor is x plus 3. So this is what we're going to be doing. We're going to be doing the original polynomial x cubed plus 2x squared minus 5x minus 6 divided by x plus 3. So let's see how we do that. So let's write this out as a division. So we have x cubed plus 2x squared minus 5x minus 6. That's the original, and we're dividing it by x plus 3. And so we want to see how do we do this. So to do this, what we do is we set it up just like long division with numbers. We have the divisor out front, so we have the x plus 3 out front, and then we write the little house, the division symbol, and we have on the inside the dividend, which is the numerator x cubed plus 2x squared minus 5x minus 6. So it's just like with regular division. We look to see, is there a way that we can put x plus 3 into x cubed? Not really, so we sort of move down to the next part. We have x cubed plus 2x squared. So we see, how many times does x plus 3 go into x cubed plus 2x squared? Or in other words, what do we need to multiply in order to cancel out like that first part? So we want to cancel out the x cubed. We want to multiply x plus 3 by something to get rid of the x cubed. And so what that is, or we're trying to match up those leading terms. So we want this to be x squared, because if we do x plus 3 times x squared, then what's going to happen with the long division is that they will subtract out and will cancel with that x cubed. So seeing what this looks like here, we have x plus 3 times x squared. And then we subtract that to the dividend parts, to the x cubed plus 2x squared. So we have x squared times x plus 3, distribute the x squared in, so we have x cubed plus 3x squared. And we're subtracting this. This is how we do long division. We want to see what's the remainder. All right, so we multiply the x squared with the x plus 3 and then subtract that from what we have as the dividend on the inside, and we see what's the remainder. But we have to remember that we're subtracting everything. We're subtracting the x cubed and the 3x squared. So what we have here left over is x cubed minus x cubed, that's 0. And then 2x squared, this minus the subtraction goes on the inside. So this is 2x squared minus 3x squared. So we have a negative x squared. So once we have that, so let's change this to be in red here, 0 minus x squared. And once we have that, we bring everything down and just do it all again. So it's a very recursive process where you just kind of keep going step by step and see now what we have left over is leading coefficient is negative x squared, or that leading term is negative x squared, and then we have minus 5x minus 6. So now we want to see how many times does x go into this negative x squared? Well, it goes into negative x squared, negative x times. Essentially, we're looking at what can we multiply x by to get negative x squared. So that result is negative x. So if we multiply x by negative x, this is what we get. So we have to multiply negative x to the entire factor x plus 3. So we have x plus 3 times negative x. And that's what we're subtracting. We're subtracting this entire expression. So distribute the negative x in, you have negative x squared, and then negative x times 3, that's negative 3x. And then from here we do the subtraction. So we have the subtraction out front, so this becomes positive x squared. So negative x squared plus positive x squared is 0. That was our goal. And then we have negative 5x, and then negative 3x here, but it's subtraction, so that subtraction goes on the inside. So this is plus 3x, so this comes out to negative 2x. And then we bring down that minus 6. So we're almost to the end. Now we just have to do it one more time to see how many times does x plus 3 go into negative 2x minus 6. Well, to get to negative 2x from x, you multiply that by negative 2. So this is negative 2 out here. So lastly, what we do is we just check to see if there is a remainder. So we have x plus 3 times negative 2. And so when we do that, distribute the negative 2 in, what we have is negative 2 times x, that's negative 2x, and then negative 2 times 3, that's negative 6, and we're subtracting this entire expression. And so we see what we have left over. This is negative 2x minus negative 2x, so that's plus 2x, and that becomes 0. And then we have negative 6 minus 6, so that's positive 6, so that's a 0. So we have a 0 remainder, which is great. Because a 0 remainder, what that means is that there is no other remainders and this divides nicely. And so what we can say here is that when we do this division, what we end up getting is x squared minus x minus 2. So thinking about what this means, and it helps to think about it in numbers. So with numbers, remember if we have something like 20 divided by 4, that's equal to 5, because 4 goes into 25 times. But we can also write a division result like this with the quotient and the dividend and the divisor and all that. We can write it as a product. We could also write this and say that 4 times 5 is equal to 20. So we can write it as these are two factors of 20. 20 divided by 4 is 5, so that means that 4 times 5 is 20. So if we have the two factors out, we can write it as a product and we get the dividend, the thing in the numerator. And so we can do that here as well. We have this long cubic expression, polynomial. It's being divided by x plus 3, and we got out x squared minus x minus 2. So what that means is that we can write the dividend, the original polynomial in the numerator, could write it as the product of its two factors. So what we have here is x cubed plus 2x squared minus 5x minus 6. So that's what we started with. Draw a dotted line to show that we're breaking this up. Is equal to, we had x plus 3, that's what we divided by, and the result was x squared minus x minus 2. And now being able to write it in this way is essentially the goal. We want to reduce down this polynomial further and further so that we can find and identify what all the factors are. Because when we pull out or divide out the x plus 3, we have left over x squared minus x minus 2. And this is a quadratic, which is great because we know how to work with quadratics. First, we can check to see, can we factor this quadratic in some way? In fact, we can factor this quadratic in some way. We want to see what two factors of -2 will add up to the middle term, the b term, -1. And we see that those factors will be -2 and +1 because those multiply to -2, but then add to -1. So we can factor this even further, and this is x plus 3 times this factors to x minus 2 times x plus 1. And so these are the factors here of this polynomial. And so what we started with is this expression here. So we can bring this down, x cubed plus 2x squared minus 5x minus 6. This whole thing we just factored into x plus 3 times x minus 2 times x plus 1. And that's really, really powerful result here that we can factor a cubic in such a way using this long division. The catch to all this, though, is that we needed to know what a factor was to begin with. Because in order to reduce it down, we had to divide out the x plus 3. We were given the x plus 3. So that is one of those drawbacks of factoring using the divisions is we need a factor already in hand to get the other factors. And we can see that these three factors that we found right here actually correspond to the zeros, right? That x is -3, -1, and 2. So we can actually say and factor what these zeros are from the factors. So now let's look at another method of finding zeros analytically, and that's with synthetic division. So with the long division, we divide it out using a factor. With synthetic division, we can divide out using the 0. And we're going to use the 0 x equals -3. That's what we were given. And so the way we set it up, it looks really similar to how we set up the long division, but we have the 0 out front. So we only write the 0 out front, and then we set up the house. We build it upside down though, and we put in here the coefficients of the polynomial. So we have, think about it as we have x cubed out front, and then x squared is the next term, x to the 1, and then we have the constant term, which is technically x to the 0. And so write out only the coefficients. We're only using the coefficients. So looking at the polynomial that we had, x cubed, the leading coefficient is 1, x squared, the coefficient on that is 2, the x to the 1 term, that coefficient is -5, and then the constant coefficient is -6. So then what we do, and it's kind of following an algorithm process like we did with the long division. So we first carry down the 1. So we carry down that leading coefficient, and then we multiply. We multiply the -3, that 0, with the thing in the bottom. And so when we multiply that, we bring that up here, and we get -3 out. So we have -3 here because we did -3 times 1, and then we add the coefficient with the product result here. So we're doing 2 plus -3. So 2 plus -3, that's -1, and then we multiply again. So we just continue multiplying by the -3. So we multiply by -3, that result here is now +3. So then we do -5 plus 3 is -2, and then we multiply that again by the 0, which is -3, and then the result we have here is -2 times -3, that's +6, add that, and that's 0, and we get no remainder, or a 0 remainder, which is great. That is exactly what we want, so we'll give it a little smiley face. Because when we have no remainder, what that means is that this divides out nicely, and we can write out exactly what the factors are. But now the question is, how do we interpret this result here, this quotient, as a factor in terms of polynomials? Well, it works out that these are the coefficients of a reduced degree polynomial. So it's helpful, I think, to start out with, on the far right, this is the constant term. So this is the x to the 0 power, and then you just count up. This is x to the 1, and then x squared. And so what that means is that we could write this polynomial out as 1x squared, which is x squared, -1 x to the 1, which is just -x, and then -2 x to the 0, which is just negative 2. So this is the result after we do the division of x cubed plus 2x squared minus 5x minus 6 divided by x plus 3. So we're doing the same division that we did on the last one, but we're just doing it using a different process. In this process, we use the 0. In the long division process, we use the factor. But the result is the same. We get this as the result. And so we can come to the same conclusion where the original polynomial, the y equals x cubed plus 2x squared minus 5x minus 6, this is equal to the factors that we have here. The factors that we have are x plus 3 and x squared minus x minus 2. So we have x plus 3 times x squared minus x minus 2. And you can always check this by just distributing the x plus 3 into the other expression. And then this factors nicely. We already talked about how to factor this. This is x plus 3 times x minus 2 times x plus 1. And so these are the factors that we got here. So this is one really useful and powerful way of factoring and then also finding the zeros, because then the zeros here are x equals negative 3 because it's just the opposite signs, and then x equals 2, and then x equals negative 1. So we can always go back and forth from the zeros to the factors. And so in each of these cases, the results produced a factor, which in this case was a quadratic. And we've already talked about how to find the zeros of quadratics. We can factor. If we're really having trouble with the factoring, we can always use the quadratic formula, and that will for sure give us the factors every time. So in this example here, what we're doing is we are doing another division, 3x to the fourth minus 2x squared plus 7x minus 12 divided by x minus 3. And you might notice that on the dividend in the numerator, it's missing a term. It doesn't have an x cubed term. There's no x cubed term. And there really is an x cubed term. It's kind of just hidden. What it means is it has a coefficient of 0. So we use a placeholder in place of the x cubed term. So when we do the division, x minus 3, that goes out front, and then we're dividing the 3x to the fourth. And then for the x cubed term, we just put 0x cubed. And then we write everything else out, minus 2x squared plus 7x minus 12. And so that's how we write out that division. We just use 0x cubed as a placeholder. And so to save ourselves from redundancy, again, let's take a look at how we do this division with synthetic division. And we're going to do the same thing. We have a placeholder. So we use the placeholder of 0 here. So remember, with synthetic division, we have the 0 out front. So we want to use the 0 here. So if we're using this x minus 3 as our factor, the 0 is x equals 3. So we're using 3 as the 0 here. So we have 3 out front, and we set up the synthetic division. Remember, this is going to be the x to the fourth term, x cubed term, x squared term, x to the 1, and then we're going to have to get a little small here, x to the 0. And so we set up the coefficient of x to the fourth is 3. The coefficient of x cubed, it's not there, so we say it's 0. The coefficient of x squared is negative 2. And then the coefficient of x to the 1 is 7. And lastly, the constant coefficient is negative 12. So with the synthetic division, remember, we carry the first one down, it's 3, and then we multiply. And so when we multiply, we get 3 times 3, that's 9. We add these together, and we end up with 9 as the result. And then we multiply 9 with 3, so we're just always multiplying by the 0. So multiply 9 with 3, and that is 27. And then you add negative 2 with 27, and you get 25. And then multiply, keep the color the same here. We'll change this 27 to red. And then you multiply 25 by 3 again. And so you get 75 here. And then you're doing 75 plus 7, and that's 82. And then you multiply 82 by 3, and you end up getting 246, and then you do negative 12 plus 246, and you have 234. Well, so what that means here is that we have a remainder. This is the remainder. We do not have a zero remainder. So what that means is that x minus 3 is not a factor of this polynomial. So we can say x minus 3 is not a factor. And additionally, what that means is that the corresponding 0 is not a 0. So that means that x equals 3 is not a 0. So this is a good way of checking if this is a 0 or if this is a factor. Another way of checking to see if a value is a 0, if something is a factor, is by just plugging it in. Because remember, with zeros, if we plug it in, we should get 0 out. That's what they mean. They're the solutions to when the output is 0. And so looking at this potential 0, we know it's not a 0, of x equals 3. If we plug that into the expression or into the function, so if we look at f of 3, we have 3 times 3 to the 4th minus 2 times 3 squared plus 7 times 3 minus 12. And so what we should end up getting here is 234. And I invite you to check that in your own calculator. Make sure to do the exponents first, 3 to the 4th, and then the 3 squared, and then do all the multiplications and then adding and subtracting. So you should end up getting 234. And then what you see is that the 234, that output result of when we plug in 3, that's exactly the remainder. So the remainder and this output result, f of 3, are the same. So we'll say they're the same. And this will actually happen every time. This is what we call the remainder theorem. So if you have r is the remainder from doing synthetic division or even long division, then what that means is that if we're using x equals, say, k as the 0, the potential 0, then we do that synthetic division with the k. That is the same result as when we plug in k into the function. So now let's look at a new polynomial that we haven't seen before, and we're told that x equals negative 3 is a 0. So this is often the case, like I was saying, is that you need to know a 0 in order to do the synthetic division or in order to do the long division. So we have x equals negative 3 is the 0. If x equals negative 3 is the 0, then that means that we can say that x plus 3 is a factor. And so we'll keep that in mind when we are writing out the factors of this polynomial when we're trying to factor this. But first, let's try to do this with synthetic division. And notice that if we have this polynomial here, and we can see that there's 4 terms, we can try to factor by grouping, but you might find out quickly that when you do factor by grouping, you can factor a greatest common factor from the first group, but the second group doesn't have a greatest common factor, and then the end results don't really match up. So we can't do this with our nice regular factoring rules. So we're going to do this with synthetic division. So we use the 0 of negative 3. So we put the negative 3 out front, and then we list out all the coefficients. So we have the x cubed coefficient, which is 1. We have the x squared coefficient, which is negative 2. We have x to the 1 coefficient, which is negative 11. And then lastly, we have the constant coefficient, x to the 0, which is 12. And so now that we have all these written out, we can follow through with the synthetic division process. So carry the 1 down, and then again, we multiply. We multiply the 1 with the negative 3, and that's the result that we get here. So that's negative 3. So we're doing negative 2 plus negative 3, and that result is negative 5. And we multiply negative 5 by negative 3, and we get positive 15. And then we add negative 11 with positive 15, and that result is 4. And then we multiply 4 by negative 3 again, and we have negative 12. This is looking good. So we do 12 plus negative 12, and we get 0. That's great. So we have a 0 remainder, which is what we want. That means that this divides nicely and we were not lied to. X equals -3 is a 0. So the result that we have here, remember, this is x squared term, this is x to the 1 term, and this is the x to the 0 term. And so we can write this out as a new factor. So this is x squared, or 1x squared, and then -5x, and then plus 4. So this is the factor that we have. And so what this means, or what we can say here, is that the original polynomial, x cubed minus 2x squared minus 11x plus 12, can be written as, we're using x plus 3 as the factor, so we just divided x plus 3 out. So we have x plus 3 was what we just divided out, and the result, or the quotient of that, is this x squared minus 5x plus 4 that we're bringing in here. So this is the x squared minus 5x plus 4. And so we can look at what we have left over here, x plus 3, we can't reduce that anymore. And so we have then x squared minus 5x plus 4. We want to see what two factors, or what two numbers will multiply it to 4 that will add to -5. Well, the two factors of 4, you can use +2 and +2, but if we add those up, we get +4, so that won't work out. But we can do -4 and -1, and those will add up to -5. And so the result we have here is x plus 3 times x minus 4 times x minus 1, because -1, -4 multiply to +4 and add to -5. So we have the factors here. So let's label that. These are the factors. And so that means that the zeros are the solutions that we have when we set these equal to 0 using that zero product rule. So what that means is that these zeros are x equals -3. We just swap the signs, or make the opposite signs. -3, +4, and +1. These are the zeros. In fact, let's give this a big box. And on this next one here, we have the polynomial 2x to the 4th plus x cubed minus 13x squared plus 4x minus 84. And we're given that x equals 2i is a 0. So remember, I is that imaginary number. And what that really means is that I is defined to be the square root of -1. So we use I, or the imaginary number I, to say this is what -1 is. And it essentially helps us to write out square roots of negative numbers. And so what that means is that we can also have this result here that I squared, if you do a square root of -1 squared, the square root and the squared cancel, so we just get -1. And so for example, we could be looking at, so let's say an example is that we could be looking at the square root of, say, -9, and we would say that this is 3i, because the square root of 9 is 3, but then you have that negative on the inside, or that -1 on the inside, so the square root of -1 is I. So that's how we use and apply imaginary numbers. So we can actually do synthetic division with imaginary numbers. So if we have this x equals 2i is a 0, what that means is that we could set it up as the synthetic division 2i, and then we would set it up, this is the x to the 4th term, x cubed, x squared, x to the 1, and x to the 0. So these are all 2, 1, -13, 4, and -84. And now this is actually kind of a longer process, and we won't be asked to do synthetic division with imaginary numbers, but I do want to talk about how imaginary numbers appear in the factors and how they appear in the zeros. So we have that this is a 0, which means you could say that x minus 2i is a factor. However, when we are writing out factors of polynomials, we usually want to write them as real numbers. We don't want to write them using imaginary numbers. So there's another way that we could go about seeing what the imaginary factor is, or what the factor is that gives us the imaginary number. In essence, you could think of it as x equals 2i. That's what we have, right? And what we could do is we could square both sides of this expression. So if we square both sides here, do x squared and then 2i squared. So we apply the squared to the x and it's just x squared. And then we apply the squared, since it's multiplication on the inside, we can apply the squared to the 2, which is 4. And then we apply the squared to the I, so this is I squared. But remember, we said I is the square root of negative 1, so I squared is negative 1. So this is x squared is equal to negative 4, because this is negative 1 here, so 4 times negative 1 is negative 4. And so if we want to set this up as what the factor looks like when we're doing the zero product rule, we would just add 4 to both sides. We want to get 0 on one side. That's how we related back to what the factor is. So what we have is this expression x squared plus 4 is equal to 0. So this is what we, in essence, started with. We're working backwards here because we had the 0 and now we got the factor. So in truth, we would say that x squared plus 4 is a factor. And if x squared plus 4 is a factor, what that means is that we have another associated factor. So that associated factor here, if we actually do this solving out, x squared plus 4 is equal to 0, we would subtract 4 on both sides, so we get this cancels out to 0, and then we have 0 minus 4, that's negative 4, and what we have is x squared is equal to negative 4. And then to solve for x, we apply the square root, that cancels out the squared, and we apply the square root here. But remember, whenever we apply the square root, we can always get two different solutions, a positive and negative solution. So here, what we actually have is x is equal to plus or minus, this would be 2i because we have the negative on the inside, and the square root of 4 is 2. So it's plus or minus 2i, which means that we have two zeros. We have positive 2i and a negative 2i. So this means that we have x equals positive 2i and negative 2i are the zeros. And so there's always this conjugate pair. We mentioned that in the last set of notes, is that if you have one imaginary 0, then you will have a conjugate or a negative imaginary 0.